Well, welcome back. I hope this is our last mini vodcast about the atomic substructure. And as we left off at the previous vodcast, we had learned that the electron had been discovered. It had a negative charge, and it was one of the three subatomic particles that we're now going to finally finish learning about. Up until that point, when Thomson had done his work, it had been thought that the atom was indivisible. Remember, you have to be responsible for atomic models, so make sure you're clear on being able to draw, sketch, and explain the Thomson plum pudding model. And if asked questions about the Millikan oil drop experiment or how a cathode ray tube functions, go back and review your notes and any other vodcasts that deal with it, because you'll probably see some questions about that as well. So what we're looking at here is an interesting apparatus. Rutherford was actually from New Zealand, but he did his work in Canada, and he's kind of a science national hero there. In that interesting twist that I talked about at the start of this unit, and that direct transmission of knowledge from teacher to student, Rutherford was a student of J.J. Thomson. So what they've been doing was research looking at how if you shoot a subatomic particle called an alpha particle in a thin beam at pieces of thin gold foil, or later on other metals were used, you can see that the particles will scatter or be deflected, and this is what they were studying. So I'm going to break it down and show you the various parts of it, and then be sure to mention the serendipitous nature of this experiment, how they got a totally unexpected result that helped identify what we now know to be the nucleus. So over here on the far left-hand side, Rutherford placed a radioactive source. On your notes, please write in the word polonium. In the first experiment, their source of radioactive particles was the element polonium, discovered by Marie Curie and named for her native Poland. Well, if you place it in a lead box, even though the particles shoot out from everywhere, if you just make a thin hole in the box and direct that through a little spot like that, should be on the box, now you'll have a beam of alpha particles that are shooting out towards a very thin piece of gold foil. Now those alpha particles have a positive charge, and relative to other particles in the atom, they're very, very fast, thousands of kilometers per hour, and they're also very massive. So they make a good bullet with which to try to penetrate the inner guts of the atom. Now, as they're shooting at this gold foil, this picture doesn't show up very well. This is actually a continuous screen that wraps around kind of like a horseshoe. So there's really no gap in between A and B and C and D and so on. It's a continuous screen. Please note on your notes, this fluorescent screen was coated with zinc sulfide. And as we learned, zinc sulfide will give you a phosphorescence or a glow as these particles strike it. Now, a lucky graduate student probably was stuck there counting how many of these scintillations, those mean flashes of light, were seen at various parts around this horseshoe arc around the gold foil. And they got to sit there and count that. So what happened then was, after Rutherford had a conversation with Hans Geiger, who of course invented the Geiger counter, they had this graduate student named Marsden. And a lot of times professors get the credit for work perhaps that their graduate students have done, but Rutherford and Geiger said, let's give Marsden some busy work, and we're going to set him to work on this project to see if we can get these scintillations or flashes of light to pass through the gold foil here and to come off not at small angles but at large angles. And then kind of like, they were telling each other, I don't think this is really going to work. But we're going to go ahead and set Marsden onto that project anyways. And what happened a few days later was Geiger came to Rutherford and said, the most amazing thing has happened. And what had happened was, yes, there were flashes of light straight ahead as the gold particles, as the alpha particles passed through the gold. There were some minor deflections and some major angles of deflection. But what was so astounding was it was as if the alpha particles had hit dead on something in an atom of gold and bounced back on a screen with a flash that was in front of the gold foil. And the historical comment that Rutherford said, which you've now hopefully seen at least twice in accompanying videos, is, "It was about as astonishing as if you had held up a piece of tissue paper," or a Kleenex in English. If you held up something like a Kleenex and looked at somebody who was going to shoot a cannon at you, a 16-inch shell, and say to him, "Go ahead, make my day." And it shot the cannon at this metaphorical tissue paper, and it bounced back and hit you. So that was what was so astounding. There were alpha particles bouncing off of the gold foil and striking back and registering with a flash on the part of the screen that was in front. Now this is very important, but let's go ahead and take a look at a cross view of what the atom of gold must have looked like. The thing about metals being so malleable is that you can make them very thin and very flat. So you can get them as much as or as few as 20 atoms thick. This is a cross view looking at atoms. So 99% of the particles that were bombarding the gold foil passed through unchanged, like you can see here at A or at B. A little less than 1%, you'd see an alpha particle come through and come off at a slight deflection. And that would be exemplified by what you can see here possibly, or maybe even over here registering on the screens at B. The astounding part was that sometimes an alpha particle would come dead in and bounce back and hit that screen with a flash that was in front of the gold foil. Now what can we conclude from this? And here is this data that is summarized. If 99% of the alpha particles pass through the gold foil, Rutherford concluded that an atom was not solid, like Thomson and his previous researchers like Dalton thought, that an atom was mostly empty space. And in fact, now I think I've mentioned this statistic before, if you put a dime on our classroom floor, the nearest electron, if that represents what we now know to be the nucleus, the nearest electron will be somewhere out on that football field. Another important concept was, if alpha particles are positive, then the only thing that can be pushing away a positive charged particle is another positive charge. And so Rutherford concluded that the center of the atom, which he called the nucleus, must have a positive charge on it. Finally, the angle of deflection had to do with how close you came, and I don't like this picture B, so I'm going to go with this picture right here. It depends upon how close you came to that positive nucleus of the atom. If the alpha particle comes in and comes close to, it kind of veers off because positive repels positive at an angle, but that would have registered on the other side of the gold foil. If, however, the alpha particle comes straight in, please understand it doesn't collide with the nucleus, because as it gets closer and closer to the positive nucleus, the repulsion force gets greater and greater, and that's the one that bounced back and was analogous to a cannonball bouncing off of a Kleenex. So this is a really good experiment in that it shows that sometimes it's the unexpected results that are the most revealing. And sadly, you hardly ever see Marsden mentioned in the history books. Rutherford and Geiger get all the credit. So what we come to then is an understanding that the atom is mostly empty space with a dense positive central core called the nucleus. Now he knew it had to be positively charged, and so we've identified in future subsequent experiments, he identified that there were protons there. It took another, like to the 1930s, for the researchers Chadwick and also the Curie's daughter, Irene Joliot-Curie, to discover the neutral neutron. Because as they got more sophisticated, the mass inside the atom wasn't adding up, so they realized there must be another particle there that added mass but no charge. So our dense positive central core, outside of which lies these electrons. And it's the whole crazy thing about these tiny bits of nothingness that move at nearly the speed of light that are going to dictate our next chapter on the atom. So that brings us to where we had stopped previously on the vodcast I had done about counting subatomic particles. An atom is mostly empty space. It has a positive dense central core, and the electrons are outside of that core. But what happened and what caused some concern is that an electron is a charged particle. And when a charged particle is orbiting around something in a curved path, it should be giving off energy, de-accelerating or decelerating, and theoretically should spiral in a death curve into the nucleus and self-destruct. Now that of course wasn't happening, because if atoms are self-destructing, then all matter around us was self-destructing. And what happened is that since this did not follow the laws of physics that were known at the time, Rutherford had a problem completely explaining his model of the atom. And who followed Rutherford was one of his students, Niels Bohr, where we will pick up again when we begin the next chapter about the atom as we explore the minute structure and the behavior of the electron. So I will see you in class next, and please make sure that you've studied and reviewed all of the experimental models, some of the experimental procedures if they exist, be able to match researchers to their correct model or their process, as well as know how to count protons, neutrons, and electrons, and be able to also calculate average atomic mass or isotopic mass. Take care until the next time. Bye.